Okay, everybody, please say happy Saturday. 1, 2, 3.
Happy Saturday!
Thank you. Okay, let's start. So I'm going to be talking about compacting GC for Ruby, for MRI. And I have to make one correction to Matt's slides. He had a question mark next to it on his slide. It should be in Ruby 2.7. So I think we can remove the question mark. I was a little bit inspired by Samuel's talk yesterday, and I thought maybe I should rename my talk to Journey to 4 million. But actually, our application uses 4 million objects when you start it, so it's already there. Anyway, I want to say thank you all so much for having me. This is my second time in Taiwan. I'm really honored to be here. So thank you so much. Yay! I hope that tonight I can eat some chou tofu. So I was actually in the immigration line coming in here, and there was like 4 8-year-old kids in the line in front of me, and they all wanted to practice English with me. So they said to me, "Do you love milk?" And I didn't want to be a bad conversational partner, so I was like, "Yes, I love milk. Do you love milk?" And they were like, "Yes, we love milk." And I think they're learning different nouns, so they said like, "Oh, do you love apples?" And I said, "Yes, I love apples. Do you love apples?" And they say, "Yes, we love apples." And they kept going like this until at one point they were like, "Do you love football?" And I don't really watch football, but I didn't want to ruin the the moment. So I was like, "Yes, I love football." And I'm like, "Do you love football?" And they're like, "No." So I had a really good time with them. So hello everybody. My name is Aaron Patterson. I'm also known on the internet as Tenderlove. And if you don't recognize me in person, this is what I look like online. This is my online me. This is a picture of my cat, Gorbachev Puff Puff Thunderhorse. I also have another cat. Her name is SeaTac Airport Facebook YouTube. We call her Choo Choo. And I have stickers of my cat, so if you want to come say hello to me, I will give you a sticker of them. And I have like maybe 5 GitHub stickers left that Joel gave me. So I work for a company called GitHub. It is a tiny startup. Maybe you have heard of it. You could say that GitHub is my active job. I'm on the Ruby core team, and I was looking at I was thinking about, wow, how long have I been on the Ruby core team? So I went and looked at my commits, and it turns out I've actually, my first commit was in 2009, so it's been over 10 years. Thank you. I'm also on the Rails core team, and I thought, I should check there too. My first commit there was actually in 2009, but I wasn't on the core team at the time. So actually, I think it might be easier to get onto the Ruby core team than the Rails core team. But I don't want to say this, like, you might be thinking, wow, that's so exciting. There's a real expert on stage, but I want you to take your expectations, and I want you to lower them a little bit. And even after you've lowered them, like, maybe go a little bit one step further. So I'm going to talk about a compacting GC for MRI, but first I want to cover some controversial features in Ruby 2.7. And Matt's talked a little bit about these yesterday. So first I want to talk a bit about the pipeline operator. What do people think about the pipeline operator? Yes, it is. You don't have to be a fan. It's fine. This is the pipeline operator, if you want to know what it is. And I was thinking to myself that, well, Ruby is designed for developer happiness. So like Mats has said this, the language is designed for developer happiness. So I decided to go in and change the pipeline operator into an emoji. So and I asked, like, I made a patch for this, and I asked Mats whether or not we could use an emoji instead, and he said, well, I don't think that people can will really type emojis on their computers, so I don't want to do that. But then I found that in Perl 6, this is the syntax for an atomic infix increment. So they actually use emojis in Perl 6, so I think maybe we should use them in Ruby as well. So you can check out this pull request here. It's actually a real pull request. I think it might be rejected now, but check it. Also, typed Ruby, what do people think? Are you excited about typing in Ruby? Yes. So, well, some people are excited, some people aren't, but I think Ruby is already typed, because how else do you get it into the computer? You have to type it. Yeah. Sorry. Okay. So let's actually move on to the real presentation. I'm going to talk about a compacting GC for MRI, and to be more like, I made this presentation title, and Koichi saw the presentation, and he's like, so Koichi is very stickler for correct names. So I had to make a correction it's much more boring. What it really is manual heap compaction for MRI, which is not nearly as exciting. But I'll talk about what that means. This work that I'm going to talk to you about, it took me approximately 3 years to complete this work. And to be honest, this presentation is about some of the most difficult code I've ever written in my life. And honestly, like, I say to a lot of people, I don't have any new ideas, but I think I finally had a new idea, and that is what I am going to present to you today. Actually, somebody tweeted about it. Chris Seaton, I don't know if you know this person, but he's one of the developers on the Truffle Ruby team. He's one of the PhDs there, and he tweeted, he said, that's me, had a novel solution for not moving objects referenced from C. Now Chris is an academic, and I need to do, like, I want to do a little bit of translation for you. When an academic says novel solution, what that actually means is that I am a genius. So thank you, Chris. I really appreciate that. So today's topics, I'm going to give you a high-level overview of today's topics. Some of them will be very technical and in-depth, but if you get lost, it's okay. I think that part of the thing I want you to take away from this today is, like, if you encounter a problem similar to something that I've discovered, my goal is that you'll know keywords that you can Google later. So I consider that my measure of success. If you can remember, like, something to type into Google, then I think I did my job. So today we're going to talk about Ruby's heap, the compaction algorithm I implemented, the implementation details, debugging garbage collector, and then the results of this patch. So first off, what is compaction? Compaction is essentially taking allocated memory and free memory and rearranging them such that the free and allocated memory are all together. So imagine that we have some computer memory that's laid out something like this. If we rearrange it like this, then we are compacting it. We say that we're moving all those allocated chunks together and the free chunks together and making them essentially one area, well, two areas, allocated and free. Now, you may remember something like this from the 90s. It's very similar to defragging your hard drive. But instead of defragging the data on your hard drive, we're actually just defragging what's in memory. So if your hard drive is messed up, we should defrag it, and the same thing with your memory. So why compact though? What is the point of actually doing this? One of the reasons to do this is for efficient memory usage. So let's say, for example, we have a layout like this, and we'd like to allocate something new. So we go to allocate it. We want to allocate something that's about that wide. Now, unfortunately, it won't fit in this free slot because the free slot is too narrow. So maybe we'll try this other area, but it's also too narrow. So we can't allocate it here, and we'll actually get an out of memory error in this case. Now, if we rearrange the memory such that all the allocated chunks were together and the free chunks were together, well, now we can actually fit that in here, and we can allocate into that particular area. So we're able to use this memory more efficiently than we could have if it was fragmented. Another advantage is CPU caches, so efficient use of CPU caches. So for example, when your program reads memory, it has to go through the CPU in order to fetch that memory from your main memory on the computer. Now, the CPU will actually read a chunk of memory from your main memory at a time and store that chunk in a cache. And as the program processes what's in memory, it'll hopefully be reading out of that cache. So say we want to read some chunk, that chunk will get read into the CPU cache, and then as our program processes, it'll read out of that CPU cache. Now, unfortunately, in this case, we get to the end of that chunk, and we need some other area. We don't want to read into the free memory, we want to read some more allocated memory. So in this particular case, we have to go say, hey, CPU, give me this address, and it'll have to go jump to a different location. So the CPU will go read from that different location, and then that data will be read into the cache, and then we continue processing. Now, this jump and read into CPU cache isn't free. Ideally, we'd like to be reading through the CPU cache all the time. So if we can read memory into the CPU cache and always be using that, then we'll be able to speed up our programs. So the idea is that if we rearrange all of our memory such that it's compacted like this, and we have no free slots in there, then we can read everything into the CPU cache, and our program can just process everything that's inside of that cache. Now, this particular, this particular, how do you say in English, tokcho? This particular trait, sorry, I forgot the word. This particular trait is called good locality. We call this good locality, meaning that all the stuff that we need is in the same location in memory. So we can copy that into the CPU cache. Now, another advantage is copy and write friendliness. At work, we use a web server called Unicorn. And Unicorn uses a copy and write technique for saving memory. And essentially, like, compaction can actually increase the efficiency of this copy and write technique. So we'll talk about how that works. Essentially, when your program forks, when it calls the fork function, the operating system will make a copy of that process for the child process. So in this example, we have a parent process, and we fork and we create a new child process, and it has a copy of the parent's memory. But it doesn't actually copy all of the memory. It creates virtual memory that points at the existing memory. So this isn't actually the case. Actually, what will happen is we have a bunch of pointers up to the real process memory. So we don't actually we don't actually increase the memory by 2 times. We just point at the original. Now, if the child writes something to this allocated memory, before the write actually happens, the operating system will copy the memory down into the child process. So what will happen is the operating system will cut that line there, copy it down into the child process, and then the child process can allocate into that area, and it doesn't impact the parent process at all. Now, a problem with this is that when the operating system copies that chunk to the child process, it actually copies a fixed width amount of memory. So if you write one Ruby object that's only 40 bytes, the operating system isn't going to copy 40 bytes. It'll copy something larger, and it's about 4K. So in that case, we can actually end up with too much memory being copied down into the child process. So in this case, we'll actually increase the amount of memory that we're using in total, but we didn't actually need to. So all of these cases are examples of problems with fragmentation in our memory, and the solution to all of them is eliminating this fragmentation. So compaction is the solution to eliminating fragmentation. So once again, this is what fragmented memory looks like. And compaction is simply moving all the allocated stuff together and the free stuff together like this. That's it. So now I want to talk a little bit about the heaps in Ruby. We can say that our Ruby programs have essentially two heaps. What I mean by this is, let's say we have a computer with system memory that looks like this. This is just our main memory on the system. When we allocate memory when we ask the system for memory, we typically use the malloc function. And that function will allocate a chunk of memory, and I call that the malloc heap. So we're allocating memory with the malloc function. Now, what Ruby does is inside of the malloc heap, it arranges a smaller area that's used for Ruby objects. And I like to call that Ruby's object heap. So inside of the malloc heap, we have Ruby's object heap. Now, when we actually allocate a new Ruby object, it comes out of Ruby's object heap. So if you say object.new, it'll come out of this area right here. Now, ideally, Ruby's object heap would be exactly the same size as the malloc heap, but that's never the case. And I'll give you an example, a very simple example of why that's not the case. Let's say we allocate a string. So a string may be variable width. It might be long, it might be short. And if it's long, we'll have to allocate that out of the malloc heap. So in the case of a string, we'll allocate a new Ruby object that represents the string, and then we'll use a character buffer allocated out of the malloc heap, and the string points at that character buffer. This is one reason why the malloc heap will always be larger than the Ruby heap. So the important thing that I want to bring up with these two heaps is that fragmentation can occur in both of these heaps. So the thing that we're going to talk about today is addressing the fragmentation that happens inside of the Ruby heap, not the malloc heap. For the malloc heap, at work we use JE-malloc. This is a separate malloc implementation, and I recommend you use this in production with your Rails applications. It's very good. Just use it. Now for the Ruby heap, we have GC Compact, which is the thing that I worked on and I want to talk about today. So let's take a look at what Ruby's heap actually looks like. So if we were to visualize it, what would it actually look like? Not the system memory, not the malloc heap, but this Ruby object heap. What does it look like inside here? So the way Ruby's memory is laid out, we essentially have fixed width slots. So each Ruby object is the same size. Each Ruby object is about 40 bytes wide, and we call these 40 byte chunks a slot. And each slot can either be empty or filled. So in this case, we'll say that white is empty and blue is filled. And later, I'm going to introduce a new color that's orange, and that means moved. So these slots are stored on a contiguous chunk, like one contiguous area. And this area is called a page. And each page is about 16 kilobytes wide. So Ruby's entire heap is actually made out of multiple pages. So we have multiple pages, and that is what comprises the entire heap. So each of these pages are actually allocated with malloc. Each of these 16 kilobyte pages are allocated with malloc. Now there's one more important thing about each of these slots that we need to know. Each slot has a unique address. So we can say that they all just have some unique number that is associated with that particular slot. So now that we know generally what the heap layout looks like, we can actually implement the algorithm. So let's take a look at the actual algorithm. The algorithm that I implemented is called a two-finger compaction algorithm, and its origins are in Lisp, and you can read about it in this paper right here from 1964. This algorithm is not a very good algorithm. And if we have time, actually, that is a very good question for you to ask. During the Q&A, you should ask me, Aaron, why is this algorithm not a good algorithm? Why did you choose this algorithm? So there you go. So the algorithm is basically has two different steps. Essentially what we do is we update the objects, two high-level steps. We move the objects, and then we update the references. So let's take a look at how this algorithm works in both of these cases. So moving objects works like this. So say we have one page here with a layout like this. Now, We point two different pointers on either end of the heap, like this. One is called the free pointer, and the other one is called a scan pointer, and we think of those as fingers. So that is why it's called two fingers. We have two fingers working on this. Now, the free pointer will move to the left or to the right until it finds a free slot. And then the scan pointer will move to the right until it finds a filled slot. And then it'll swap the two, like this. Then it leaves a forwarding address. So it says, okay, whatever used to be here in slot 9, it's now in slot 4. So it'll leave a forwarding address here. So you need to look in slot 4 for this data now. Then we repeat this process. So the free pointer will move until it finds a free slot. Scan pointer will move until it finds a filled slot. Then it swaps, leaves a forwarding address, and we repeat this process until both of the pointers meet, and then we're done moving. Now, once we've moved all of the objects, we have to update the references. So for example, let's say we have the same layout here with references that look like this. This is before compaction. So say 1 references 6, 2 goes to, 9, 3 goes to 8. So when we move it, it'll look like this, and clearly those references are wrong. We have to fix them. So the way we do that is essentially we just go through and look at each object and say, hey, what are your references, and do they need to be updated? So in this case, A points at 6, and it doesn't need to be updated, so we continue on. We look at B, it points at 9, but that needs to go to 4, so we update it and say, okay, you need to point at 4 now. Then 3 goes to 8, which now needs to point at 5, so we update that one. And then we just repeat this process for all of the objects in the heap, looking at their references and updating them as necessary. So once that's complete, then we can do one more GC to remove these forwarding addresses, and now they're converted back to free slots. So there's our entire compaction algorithm. So I translated the actual movement part into Ruby, and this is what the code looks like for doing the movement. And you don't need to read this too closely. I'm going to point out the important parts. Essentially, up here, we just loop until we determine whether or not those two pointers have met. Right here, we have a chunk that copies and leaves a forwarding address. And then down here, we move our free pointer. So we advance the free pointer, and then we pull back on the scan pointer. And we just repeat this process until the two pointers meet. Now, if we were to translate the reference updating code into Ruby, it would look something like this, where all we're doing is looping over each of the objects in the heap and then updating the references for those objects. Now, if we just look at this Ruby code, it looks like updating references is actually much easier than moving all of the objects. And actually, that's not true at all. If we look at this code here, this is actually hiding lots and lots of complexity. How do we determine what references a particular object holds? So for example, how do hashes hold references? How do arrays hold references? How do objects hold references? How do regular expressions hold references? How do structs hold references, et cetera, et cetera, et cetera. We have to know how all of these objects actually hold references so that we can update them. So this is actually the most complicated part of this patch, and I'm going to show you the code that I wrote for updating references. This is the actual code right here. Let's see the entire thing. So that is all the code. It's just that easy. So I didn't count exactly, but I would say that probably updating references is maybe 80% of the code that I had to write for this patch, and it is actually the most difficult piece and source of bugs in the compaction algorithm. So since reference updating is so difficult, I want to talk a little bit about it. The main issue that we have to deal with for updating references is supporting C extensions. If we can't support C extensions, then this is a non-starter. We can't use it because lots of folks have C extensions, including us at work, and they need to work with newer versions of Ruby. So I came up with a scheme for supporting C extensions, and I don't think this scheme was introduced before, so I'm going to introduce it now. The issue is the most difficult thing, as we discussed about updating references, is trying to figure out where they're stored. Now, let's imagine today, all of us are Ruby core team members. We're all on the Ruby core team today. Yes. Yes. Now, we're writing this compaction algorithm and we're saying to ourselves, okay, we have to update all of the references for an array. We've moved references, we've moved all the objects in an array, and now we need to update those references. And that's actually pretty easy for us because all of us, we can go in and read the implementation for arrays. If we go in and read it, we can see that an array points at a buffer, and that buffer points at a list of objects. And because we know how those objects are stored, it's very easy for us to go in and update them. So we can actually do the same thing for hashes too. We say, well, we need to know how hashes store values, and we can go read the implementation for hashes, and now we know how all these references are stored. And we can all repeat this process for all of the classes that are built into Ruby, like strings, classes, symbols, modules, etc. We can go read the source code for them and know how they keep references. So since we know that information, we can teach the GC how to update those references. In other words, the GC can update all known types. So all of these types that are known to us as Ruby core team members. So known types are types that are implemented by Ruby. So that leaves the question, what about unknown types? And I consider unknown types to be types that are implemented in C. And I'm going to give you a concrete example. This is from a C extension that we use at work. We use a JSON parsing library called YAGL, and this is the struct that's used in that JSON parser. Now, we don't need to know how the parser works necessarily, but we can see here in the struct that it actually contains two references to two Ruby objects. Now, the way that this parser works is, at runtime, we use malloc to allocate one of these structs, and then we have Ruby allocates a T data type object, and that object points at this malloc struct, so that T data comes out of our Ruby heap, and this malloc comes out of the malloc heap. Now, that malloc data, it points at two other Ruby objects. So we don't know what those are necessarily, but we know that it points at those two. Now, the issue is the GC doesn't know anything about this struct. It doesn't know the layout or anything. So it doesn't know about these two particular references here, so it can't update them. Now, the problem is if the garbage collector decides to move a Ruby object, let's say we move this one, now when the JSON parser goes to access that reference, it's going to blow up and the whole program will crash. Yes, keynote. Now, how can we prevent this type of crash? And there's a very, I guess, somewhat simple way of doing this. The way that we have to do it is we have to rely on the fact that the JSON parsing library needs to keep these references alive somehow. Like it needs to tell Ruby, hey, I have a reference. If it doesn't tell Ruby it has a reference, then maybe Ruby will GC those references, will collect those references, and they'll go away. So the way that it tells Ruby is it uses this function called rbgcmark, and it'll actually mark both of these things. So what we can do is we can say, well, when an object is passed to rbgcmark, we just don't allow those objects to move. So we say, those two can't move because they've been passed to rbgcmark. So we can make a simple rule and say anything marked with rbgcmark cannot move. So let's make an example here. Here's our heap layout. The way that we actually implement this thing is through a table that I call pin bit table. So we say that when an object is passed to rbgcmark, it's pinned. So for example here, during the mark phase, we'll go through and mark all of these objects. And in our Ruby code, in this example, we have an array and it points at two strings, and then we have our JSON parser that has two references to unknown objects. So in this case, when the mark phase completes, YAGL will use rbgcmark on those two references, and then we'll put a bit in the pin bit table to say, hey, these things cannot move. Now, the array, it will use something else. It uses gcMarkNoPin. It's a private function. And this private function marks the objects but does not pin them. So we know that we need to keep them alive, but we know that they're okay to move. Then during compaction, all we have to do is we use the same algorithm, but we also look at this pin bit. So here we scan forward till we get to a free area, then we scan backwards, but we see that's pinned, so we don't move it. We just move on to the next one, then we swap those two, and we continue on with the algorithm as usual. Yay. Now when we go to update references, the garbage collector doesn't know how to update references for YAGL, but it doesn't need to update any of them because we've guaranteed that they cannot move. So it just moves on to array, it fixes up the array references, and then keeps on moving as normal. I made this too slow. All right. So known types use GC mark no pin, and unknown types use RBGC mark, which is our public C API. So one more thing I wanted to add was allowing movement in C extensions. And to do this, I'm going to introduce 3 new concepts. One is a compaction callback, the other is no pin marking, and the third is a new location function. So as we said earlier, the GC can't update a C extension. However, a C extension can update itself. So the C extension knows its own internals, so we can let it update itself. So let's go through and actually update the YAGL extension to support compaction. So here is what our C extension looks like before we enable it to support compaction. Here we have to tell it, we have to give the GC a mark function and a sweep function. Those are callbacks. Now, in order to give this compaction support, we just add a new compact callback. So we'll update this code to include a new compaction callback here. And this function will get called every time the GC does a compaction. So it'll say, hey, we're going to call your compact callback and give you an opportunity to update your references. Then we'll update the mark function. So above is our old marking function. It uses RBGC mark and that pins things. So instead we'll use this new function, RBGC mark no pin, which is not a good function name. I am going to change the name. If you write a C extension with trunk Ruby today, don't use this function. But it will not pin those references. So the next thing we need to do is just implement our compaction callback. And all we have to do here is we say, okay, we're gonna ask the GC, hey, what is the new location for this thing? So this function will just tell you the new location and you can update your reference. Now there is a known issue with this, and I'm gonna show you the known issue. This is kind of an annoying issue. We have let's imagine we have an object graph that looks like this, where we have three objects. One of them is an object implemented in Ruby, the other is an object implemented in C, and they both point at a third object. Now, the relationship, let's say this relationship was set up by the same library. So the author may know that, hey, this Ruby object, that Ruby object on the left keeps that other object alive. And because that Ruby object is keeping it alive, I'm not going to mark it from the C function or the C object at all. So I call this type of reference a hidden reference. So the author may think, this is automatically marked, so I will not mark it. It is not marked here. Now, the issue is that let's imagine we go through the compaction process with a relationship like this. So let's say it's set up in the heap like this. We have 2 objects, they both point at the same thing. One of them is a hidden reference and we don't know about it, and the other one is just a regular Ruby object reference that we do know about. So when the compactor runs, this object won't get pinned because we just say, oh, it's fine. We'll move the location and then we go to update the references, and the Ruby object, it will get its references updated. It works, it's fine. But the C extension, it won't get its reference updated because the GC didn't know. So then we'll clear out that address and finally the program will crash. Yes. So maybe this issue isn't that common. I found it in 3 different places, and I'm going to show you the 3 different places I found it so far. One of them was in Ruby's instruction sequences. I'm not going to go too far into depth here, but essentially, when Ruby code gets compiled, for example, this method, that literal is actually a Ruby object. This is what's really one thing I actually find really cool about Ruby internals is so much of it is actually implemented as just Ruby objects, though you have to read C to learn that, unfortunately. So anyway, these literals are actually Ruby objects, and they used to be added to this thing called a mark array. Now, the instruction sequences themselves would also point at that literal object. So we'd have two references, one that was marked via the array and the other one that was not marked. So this is very similar to our previous setup. I introduced a patch called direct marking in Ruby 2.6 that essentially all it does is eliminate that array and mark all of the objects by disassembling the instruction sequences. So rather than having this third object responsible for marking things, we directly mark them. And now the garbage collector knows about this reference, or knows about the relationship between these two objects. So the good news from this is that we're able to teach the GC about the relationship, and also we're able to eliminate that array. So Ruby 2.6 will actually use a little bit less memory. And also our references won't blow up. Another place I found it was in the JSON extension, and it had exactly the same issue, the same graph as before. And one thing is that's interesting is, since this relationship on the left, since that's done in Ruby, I can actually write a Ruby program, a pure Ruby program, to cut that relationship. And if I do that, then the garbage collector will actually collect this object, and then the program will blow up. So I'm going to show you exactly where the issue was. This is the issue. What it does is it says, I'm going to get these constants and assign these constants to global variables. So the way that I cut these, or the way that I made this segv is I said, okay, I'm just going to cut this reference by removing the constant. And if I remove the constant and start the garbage collector, then JSON will segv. So the fix is actually pretty simple. We just say, hey, we need to mark these objects. So they stay marked and everything works fine. Message pack had exactly the same issue. I was able to cut this relationship here, and it blew up. And I think the argument here is that pure Ruby objects, or pure Ruby, shouldn't crash. So if I can write a pure Ruby program and your C extension segvs, that's a bug in your C extension, in my opinion. So what actually falls out from this is that we have a really simple rule to follow, and that is, if you hold a reference, you must mark the reference. That's it. That's all you have to remember, just one consistent rule. If you hold a reference, you need to mark the reference. Now, one thing I want to talk about now is actually debugging garbage collectors, and I think that this is not a very popular topic. Garbage collectors are not very easy, and there are a lot of papers on implementing particular algorithms and stuff, but I think that's really popular among researchers, is how to, the theory of garbage collectors, actually implementing them is not that popular. So there are not many academic papers on fixing garbage collectors. So I want to talk a little bit about how I was able to debug this, mainly because I want all of you to become GC hackers too, so that I don't have to do it anymore. So let's take a look at this problem code. This is some problem code. It's very similar to the one that we saw in JSON. So all we're doing here is we have a global variable in C, and this global variable points at a Ruby object. And the garbage collector doesn't know how to update global C variables, so we have a bug here. So what can happen during compaction is, since the GC doesn't know about it, it can't update it. And if it moves, maybe it moves over here, we change that to a forwarding address, and of course it gets cleared out. And then as soon as we try to use that global variable, everything blows up again. Now that's one manifestation of the bug. Now let's look at a worse manifestation of the bug. Let's say we have the same setup here. So just exactly the same as before, but it moves, right? It leaves a forwarding address, and that forwarding address goes away. Now, before the global variable is accessed again, let's say another Ruby object gets allocated. But let's say that Ruby object gets allocated here. Now all of a sudden we have a global variable that's pointing at a real Ruby object, a real valid Ruby object, but it's the wrong one. And maybe we don't know that. We just get a weird exception that's like, oh, this method doesn't exist on bar. And you're like, what? Where? Where did that come from? So I think that this particular error is way worse than the previous one. I would much rather the program just crash and die than access the wrong object. So there's three major techniques that I use for debugging this, and I want to show you the major techniques. The first one is maximum chaos. So essentially, what I want to do is if an object can move, we want it to move. We want to introduce as much chaos into the system as possible so that we can get these things to crash. So the way that I did that is I doubled the heap size. So you would say, okay, whatever the size of the heap is, we're going to double it. So it'll use twice as much memory. Then we'll perform compaction, and everything will compact towards the empty side of the heap like this. And this guarantees that all objects in the system that can move will move. And if this seems familiar to you, it should be. This is actually very similar to a two-space collector if you know GC technology. So remember this word to Google later. The next step, the other technique that I use is something called zombie objects. And we have actually, if you look in Ruby source code, there's another type of object that's a zombie object. Like this is different. So let's say we have this same compaction issue here, exactly like we showed before. What we would really like is for it to crash in this case. This is the best crash solution. We want it to crash here. We don't want it to crash here. This is bad. So if we move this over and this becomes bar, this is a bad situation. So we want to prevent this from happening. So how can we avoid this from happening? The way that I decided to do this was make it so that these forwarding addresses can never be garbage collected. So what will happen is we'll swap those over there and we leave a forwarding address, and that forwarding address becomes a zombie object, and that object can never be collected. Now, the third technique that I use is something called address sanitizer, and this is actually a compiler extension that ships with Clang. And this thing has two features. Essentially, it has a custom allocator and a compiler extension. And the compiler extension, what it does is it inserts a little tiny bit of code anytime before you read or write to memory. So, for example, let's say we have this C code here. We're writing to the address of foo. If you compile with address sanitizer enabled, essentially what it'll do is it'll insert a check right before it. It'll say, hey, is this area of memory poisoned? If it's poisoned, then we're going to blow up. If it's not poisoned, then we'll continue. So what I can do is, in this case, we'll say, okay, we have this compaction bug here. We move. It becomes a zombie address, but it's also a poisoned address. So any reads or writes to that address will automatically make the program blow up. So the way you can enable this in your C programs is with these compiler flags, and then anytime you want to poison memory, you can use this function, and it allows you to poison arbitrary sizes of memory, which is really nice. So stuff to Google, two-space collectors, zombie objects, and address sanitizers. So I'm going to go through one more challenge, and then we'll wrap this up. So I want to talk about one more challenge, which is object ID. In general, direct memory access prevents movement. So let's look at how object ID is implemented today. This is fun. Fun in air quotes. By fun, I mean not actually fun. So object ID is actually based on the location of the object in memory. So in these examples, we have object ID of 1, 2, and 9. Okay. Now, what happens if the object moves? So let's say 9 moves there. What should the address be, or what should the object be? Now, the answer to this question depends on the code. So let's take a look at some code. So let's say we have an object like this. We compact the heap and ask for the object ID. So it goes like this. Allocate an object. We compact the heap. 4 moves to 1. We check the object ID. We've never seen it before. It's fine. It's object ID 1. Cool. So let's try again. Let's say we allocate an object. Now this time we check its ID, and in this case it's 4. We compact the heap, but 4 moves to 1. So what should the object ID be? Well, I think that most of you would be surprised if the object ID changed. So we don't want it to change, so we have to do something to prevent it from changing. So in this case, what I did is I said, all right, we're going to record the object ID that you saw. So we do this by keeping a global hash. This is basically the code that I wrote, but in C again. So let's see how this works. We create an object, check its ID, we insert that into the hash, we compact, then when it moves, we can update that hash table to say, well, the object in location 1, it actually points at 4, so this thing returns 4. So our object ID is 4. Now let's have a worse example here. Let's say we do this, we move objects around, we compact it, we check it, it's 4, that's good. But let's say we allocate a new object, and unfortunately this object is allocated in slot 4. What should the object ID be? Not 4, right? Can't be 4, so what do we do? In this case, what I said is okay, we will just check to see if there is one larger. Can I use 5? If not, can I use 6? If not, can I use 7, etc., etc., etc. So in this case, we'll go through, okay, do this, we'll compact the heap, check the object ID, it's 4, we create a new object. Well, okay, so we check is 5 okay? Yes, 5 is okay. So in this case, it's 5. Now, the third thing we have to do is we have to clean up on GC. So as soon as anything gets garbage collected, we need to remove it from that table. So what I'm actually trying to tell you today is don't use object ID. I'm kidding. Like, go ahead and use it. It's fine. It's really, don't run out and change all of your code. Just like now you know that it's kind of a pain. So let's take a look at actual impact of this patch and then wrap up. So this is a basic Rails application. This is if we graph the memory. Now we all know what the memory layout looks like. So I'm going to describe it here. Each of these columns is a page that we talked about earlier, and each of the dots is a slot. Okay. The white squares represent free slots, the black squares represent filled slots, and the red ones are pinned slots. So this is before compaction, and you can see it's pretty fragmented. Now after compaction, it looks like this. So you can see they all move together. And this graph was actually generated with the first implementation I got working. So we're going to take a look at GitHub's Heap too. So this is running against our web application. That top row is before compaction and the bottom is after compaction, and it does not fit on a slide. So I did this, say, oh, okay. So you can see it moves it in somewhat. Now, oh, I forgot to mention back on this slide here. So this one, it's hard to see, but this one is actually skinnier than this one. So this one is more narrow. And what that means is we actually were able to reclaim memory from the system. So here's GitHub's heap. Okay, we saw that. Cool. So this is actually 3% pinned. 3% of our heap is pinned. And I worked a bit more on this, and this is after some updates. So again, red dots are pinned ones. Okay. And the top one is before and the bottom one is after. And you can see there are not as many red ones in here. And if we look at the impact in this case, we'll see it actually looks a lot better, right? Now, this is actually with 1% pinned. And I did some more work, and I was able to get it down even further. This is, again, top and bottom. If we compare the two here, you can see it actually has a really large impact in this case. So we're able to, in this case, we're able to get it down to about 0.3% of objects being pinned. And what this actually translates to is a 10% smaller heap. So that's the amount of memory we were able to save. Future plans, so I want to talk a little bit about, actually, no, clap for this. This is good. Thank you, yes. So I want to talk a little bit about future plans. First off is performance improvements. Right now it's extremely inefficient. It takes about 3 seconds to compact our heap. It's inefficient because it has to do a full GC, which involves 2 scans of the heap. It has to move objects, which is a 3rd scan, has to update references, which is a 4th scan, and then it does a full GC again, which is a 5th and 6th scan. of the heap, so it is very slow. But I think we can just eliminate that last one, just straight up remove it. Also, I think what we can do is instead of doing a full GC before, we just need to do this after the GC normally executes, so we can eliminate that step too. And then these two steps here can actually be combined into one, so I think we can get that down to one. The next thing I'd like to do is change the algorithm to a sliding compactor. So for example, this type of heap, instead of what we saw before, it would move more like that, where it slides down. And the reason I want to do this is because it provides us with better locality. Another reason is it supports variable width objects. And the reason I'm excited about that is because variable width objects means that we can support variable width allocations. So maybe instead of allocating everything with malloc, we could allocate it out of Ruby's garbage collector. So I want to wrap up by saying that we're constantly improving Ruby, the Ruby language, the GC with Vim, or in the VM with JITs, etc. And I think that right now is probably the most exciting time to be a Rubyist. I think Ruby's future is extremely exciting, and I'm glad that I was able to work on this thing. So that is the end of the presentation. Thank you, and thank you all for having me here today.
Thank you very much. Do we have any questions from the audience? Oh, yes.
If you use data struct in your C extension, does it just work?
If you use what?
The data struct thing.
Oh, I mean, it does just work, but it doesn't support compaction. So you have to add the callback to do it.
Okay.
Okay.
Oh, sorry. Did I steal someone's turn?
Yeah, yes, you did.
Yeah, thank you. Thank you for asking that. So the question is, why is the two-finger algorithm bad? The two-finger algorithm is bad because it only works with fixed width slots. The entire algorithm depends on the fact that all Ruby objects are the same size. So that's one bad thing about it. The other bad thing about it is that it results in objects being placed randomly throughout memory. So you can't predict where they're going to go exactly, and that's bad for locality. So when we saw the sliding compactor example, like let's say we have an array here. So you can imagine when you create array, all the elements of the array are probably going to be right after it in the heap, right? So a sliding one will move those all closer together, and they'll be in the same area relative to each other, where the two-finger algorithm will not maintain that. Yeah.
Great.
Ah.
Do we have any more? Yes.
We sometimes need the object ID to test the identity between two objects. So do you have any recommendation to replace the object ID?
No. Actually, one thing I want to do is I hope that I can finish this before 2.7 is due. But I think what we can do, the reason we have to keep track of all that junk is to support ID to ref. But I think Matt's approved getting rid of ID to ref, or deprecating ID to ref. And if we do that, then creating an object ID should be like very, very simple and cheap. So yeah, I mean, go ahead and use it. It's fine.
Okay, do you have any more questions? Any more questions?
After you do some compacting, you have to deal with such kind of things. So if we could do some optimization in Patterson, is it possible to do some work when you
Yes. The answer is yes. If the only reason we need those tables is in order to support ID to ref. If we just what we should be doing instead is just using a counter that increments forever. Just every time, if you ask for an object ID, we'll just increment this counter, and then we just keep doing that forever.
Okay. Oh. Sorry. Yeah, just press that button.
If we rewrite JSON library to Ruby, so can we get the memory benefit? And how about performance of that?
Mats, I don't know. Can we?
Yeah, we need to measure first.
Yeah, I mean, maybe we could once when the JIT, if we could with the JIT, basically, but today probably not.
Yeah, thank you.
So was there any performance improvement at GitHub by this change?
We didn't see any performance improvement in terms of speed, but we see performance improvement in terms of memory reduction.
Great. Do we have any more questions?
Is it talking about the object ID? Is it necessary to give us object ID by memory location?
No.
Otherwise, maybe using UUID is a good idea.
Yes. Yes. So the reason that we had, like, I don't know if everybody knows the ID2ref function, but basically what it does is you get an object ID. With an object ID, you ask ID2ref for the original object and it'll return it to you. And that's why the address is important. So if we don't have that function, then we can just use a UUID or any unique ID for the object.
Thank you. Great. Do we have any more questions?
Also, remember, I have cat stickers, so if you want to come say hi and ask questions later, you can. It's fine.
Hi, I would like to ask two questions. So first question is, so after Ruby 2.7, do we still need to use a gmalloc?
Yeah, so yes, we do need to still use JEmalloc. Well, we will have to use it. GitHub will have to use it because it deals with fragmentation in the malloc heap. But like, I guess my extremely long-term plan is if we can start allocating stuff out of Ruby's GC rather than with malloc, eventually we won't need JEmalloc anymore.
I see.
But yeah, for the foreseeable future, yes, you need JEmalloc.
I see. And the second question, sorry, it's a little bit unrelevant. But I think my question is, I'm curious about, because I think many people they try to with different gmalloc versions, but right now it seems like the most effective version is 3.
Yes.
And so I'm just curious about, do you know why 5 or a later version doesn't really work well?
I think it's, so I don't know for sure, but I think it's to do with threads, like managing the heaps among threads, but I'm not totally sure. But yeah, we definitely use JEmalloc 3 in production.
Great. Well, thank you very much, Aaron.